time for the next lecture, which will be convened by Henric. So Henric, the floor is yours.
Yes, thank you. I'll start by sharing my screen. So I hope you all can see that and can hear me well.
Yes, yeah.
Good. I'm going to talk about a little bit about serial R today, and why I'm talking about serial R regarding in this course where we're talking about parallel computing R is mostly because I want to prepare you for tomorrow. Because tomorrow, a lot of some of the functions we're talking about today will be applicable tomorrow as well, but in a parallel capacity instead. And also for you who have not used this functionality, I think it's a good way to show you how it works, because these are functions in R which are optimized, which work really well on list matrices, and perhaps it's not what you have been doing. Then I want to say also, I forgot to mention, my name is Henric Zazzi, and I'm working at KTH. I am bioinformatics application expert. I'm also the coordinator of application expert in Sweden. And as I work on KTH, I have no greater knowledge of Kebnekaise. But as mentioned by Pedro, we have the Dardel computer at KTH, which is quite big. And in this presentation, I will not go through that much, but I have included a lot of stuff regarding how to install packages on our cluster, but also to install packages and libraries on the Dardel cluster, as well as submit jobs. So I think that will be really handy for you if you want to, for example, run on Dardel in the future. So, as I said before, this is a brief overview, and lots of these presentations focus on how to run R in parallel on Dardel and how to install packages on Dardel as well. But main part of the presentation will be function in R for spinning up execution. And that is what we'll be focused on in this presentation. So we'll skip ahead on all these slides. Oh, this could be handy though. This is an example of how to run in R on Jupyter Notebook if you want to run it on the Google Colab Notebook. So you can look through that here if you're interested in running on Google Colab, which is quite nice because you can get access to, I think it's about 16 cores, something like that. You can test it to run and parallelize your code if you have access to faster computers. But let's skip ahead and go instead on the stuff that I want to talk about. Functions in R for spinning up execution. And in the introduction to parallelization before, Pedro was talking about scaling. And this is a plot he showed in his presentation about scaling as well, and I'm showing it again. And to achieve scaling in R, you have to know how to time your functions. And there are several methods of timing functions in R. And here I go through some of them. And method one is you kind of use a variable to record your starting time, which is the sys time. And then you write all your code here. And then you print afterward sys time minus the start time. And you'll get exactly how many, what the time has passed between those two occasions. This could be also be very handy if you remember that we talked about Amdahl's law before. And if you want to highlight or look at how many what time has passed between a certain part of the code. You could put this start and end on certain part of the code as well, and to really fine-grain, see what part of this code is taking so much time, and also look at what part of the code could be parallelized and evaluate if you need to parallelize the code, because perhaps the part that is non-parallelizable, it's so big, it takes so much time, so it's not really worth it. The other code, the method I want to share with you is the print system time, and then you put all your code in brackets, and then also print out the system time that has passed for that specific part of your code. But something I want to mention is also microbenchmark. Microbenchmark is a library or package in R that is specifically targeting how to time your functions in R. It's not installed by default, so you have to install it yourself. And when you do that, you can just write library microbenchmark, and then you have microbenchmark like this, and you have brackets, and you put all your code between those brackets, and then R will benchmark your code. In this case, I put all the results in res here as well. By default, microbenchmark run your code 100 times, and then it evaluates and kind of calculate some statistics on those 100 times to see how fast your code is. And if you think 100 times is too little or too long, you can set the flag times equals n, meaning how many times you want to run your code. So you can just write comma my times equals 4, and then you run it 4 times instead. And then, as said, it will output the statistics of your code. It will show you both the mean and the median and the first quartile and so on, a lot of statistics. And if you want to instead use the statistics and print it out in a more perhaps visually better format for you, you can instead, this is an example, only getting the average of the computing time. So then you put, in this case, I take this example here, res, and I take the summary of res, and then I output the mean. So this will just show you the mean of the code, that the average, you could say, of the code that I have added here. So this is how you time your code, and this will be very important in when you are parallelizing your code, to see if you get your code more effective, at what level of how number of processes your code is effective, and at what the number of processes, the effectivity or the performance of it will decline. So after this, I will talk a little about other functions in R that we will touch upon more tomorrow, which are easily parallelizable. And that is the apply function collection. If you're not familiar with that, apply executes a function, we call it fun, to element of variable x. And it's a compiled automation, meaning we don't do a for loop, because apply will do that for us. And it works on internal and user-defined functions. By that I mean you can use an internal function, which is like mean, for example, or you can do your own function and use it in apply. So how about an example? If you look here, I have an example. We have a list of vectors. And this list of vectors is from the CO2 dataset, which is available in R by default. And what I do here is I split the CO2 dataset into pieces of 12. And that is because it's the default dataset of CO2 concentrations in ppms, part per million, from 59 to 97. And it has monthly data. So I split it by 12 because I want to divide it by the year. And after that, I kind of name all the columns from 59 to 97. I can actually show you how it looks like. If you can see my RStudio here, if you look at CO2 like that, and then you get all the data here. As you can see, it's by, oh, by the way, can you see this? Or is it too small?
Yeah, I think we can, well, I can see it fine.
Good, thanks. And as you can see here, it's separated by different months, and it has CO2 parts per million from 59 to 97. So then I kind of split that data set into X and then name the columns from 59 to 97. So in this case, I have created a list of one item is one year of data. So what you could do is, if you normally do in programming, you do a for loop. So I'm using a for loop to calculate yearly mean of X, and I do for in the iteration variable in X, my data, and then I print the mean of each and every list item here. So how do you do that in using lapply? Lapply, instead, you can use lapply to calculate mean of X by this. So lapply kind of iterates automatically through the whole list, and then it prints the mean of X for each list item by just using that command. And if you want to check it, you can also, I don't know if this data set is that good, because if you take a bigger data set and use lapply, you see that it's faster than doing for, or should be faster than doing for, because it's more optimized towards efficiency and performance. So, lapply is, as I said before, is a several functions, and there are several functions in the lapply family, you could say. There is a function goes. They all work the same way, but they have different objectives and inputs and outputs. There is a normal apply, which you can steer. You can add kind of objectives here, like m equals 1 or m equals 2, or m equals 1 and 2, and then you can apply it to rows or columns, because the apply function here, the first one here, just has input as data frame or a vector. So then you can say to it, well, apply this to all rows, apply this just columns, or both. And then it will output your results in a vector, list, or array, depending on what you're choosing here. Why I showed lapply first in my example is because lapply is what is actually used in the parallelized function we'll go through tomorrow. And therefore, I thought to show lapply as an example was a bit better fit. Lapply, as I said, is that it applies the function here to all elements of the input X. So the input is list, vector, or data frame, and the output is list. So you get a list of all your data. So, for example, I think we can go back and run that. Oh, sorry. Let's see here. Let's see here. So, for example, if you go back to RStudio here, if you want, I'll just get RStudio in here, and then I'll show you. I split that.
Henric, can you make a little bit bigger font?
Yes, I can do that. Just wait a minute. I'll just write it up so I don't. I'll show you later how it looks like. Oh, sorry. Now it's bigger now, or does that suffice?
It's not bigger.
It's not bigger. Let's see here, and then I'll just increase it.
It's in view, yes. That's
Now?
Good, thank you.
Good. Now I can see the X. I split the data, and if I run it now, you see that it split into 39 different years. So I'll just write call names and just name all of this to something that it's easier to name. Okay, why not? Did I read wrong? Strange. Oh, that's really bad. Oh, and then if you write X now, you see the all name in the year number. So when I want to write now is I write Lapli on the data set, and I use, for example, and I say I want to run mean. And if I do that.
Now we don't see your bottom row, sorry.
Okay. Strange. Let's see like that. You see my bottom row now?
Yes, thanks.
Good. So now if I run, perhaps you didn't see, I wrote too fast. I named the rows according to the years. And now I run Lapli on it, like that I showed you. And when I run it, it will kind of show me all the years here and output the mean of the CO2 concentration on that specific year. So this is how you run Lapli. And also, I wanted to say that Lapli is sometimes used for example, there are wrapper functions around Lapli, which are using Lapli a lot under the hood. And this is an example of a function that does that, and that is a replicate function. And that I wanted to mention it because this is a very easy method to multiply your data for additional analysis. For example, if in this case I use the replicate function, I want 10 replicates of a specific data set, in this CO2, for example, and then I write replicate 10 times the CO2 data set, and then it kind of create 10 copies of the CO2 data set for me. And also then you can output here what kind of output you want to do Y. For example, if you write simplify F, then you get a list of 10 list items of the CO2 data set, and you write T instead, you get an array, a two-dimensional array of this data set. So that is all I wanted to say today regarding serial functions, but I still would like to, I have a lab for you here, which will go through here. Let's see. And so I want you to get acquainted with this kind of functionality, because what you'll do today will also be basis for what you'll do tomorrow in some part. And therefore, the task at hand up until the end of this course today will be to calculate pi using a Monte Carlo method. And what you do in this case, this is a picture symbolizing it. So you randomize a number x and y between 0 and 1. And this is y, and this is scale. And here you have the kind of a quarter of a circle. And you can see all the small dots are examples of randomized values in this. And then you calculate the distance from Origo by using Pythagoras. And then you see how many count values have distance, which is less than 1, meaning that they are in this black quarter of a circle. And then you multiply by 4 to get pi. So this is a way, if you're not acquainted with it, to calculate pi, which is a really good example for parallelization, and we'll be using tomorrow as well. So I don't want you to do all the functions. So I added here the code on how to use this functionality in R. In this case, this example here calculates randomizes 100 numbers on both on Y and X, and then it creates the Z vector to create all the length or distances from 0, and then it looks at which of those are less than 1, and then it see how many there are, and then it multiplies by 4 by the length, the total length of Z. So this is something we could do today, I think, and your lab in this case will be to implement this function calculating pi using one of the apply functions. I would recommend you to use the Lapply function because we'll be using that tomorrow. But also I would like to say to you that you are not forced now to use the Kebnekaise-R. If you want to run on Kebnekaise-R, I think that will be a great experience. But if you want to run it on your local R studio desktop, that is fine as well. And then the second part of the lab, I want you to time your code by, like I showed you before. So you can time your code either by using microbenchmark package or by using the system time. Any questions so far?